Hello, my name is Anna Evans, and I am going to introduce you to WaterTAP3 today. WaterTAP3 is a techno-economic analysis tool used to evaluate water treatment trains and enable a secure water future. I am part of the 2019 Advanced Energy Systems cohort at Mines and NREL. My research is in the treatment and reuse of water, and today I'm going to be talking about the modeling tool that I'm helping to develop. It will support increased water reuse and enable more informed water investment decisions. I will be explaining the creation of NAWI, which is the alliance that is supporting the tool, describing WaterTAP3, sharing a case study, and presenting future steps in my work. So NAWI, or the National Alliance for Water Innovation, is funded by the Department of Energy. It was created in recognition that water is vital and that we can treat and reuse our water supply, and this will help to increase future water security. So the project started about a year ago and has 3 more years until completion. And the overarching goal is to reach 90% pipe parity for the treatment of non-traditional water sources. So this means making new treatment technologies and doing that at the same cost, energy use, and recovery rates as our traditional water treatment systems today. So starting at a low technology readiness level, NAWI's goal is to develop new or improved water treatment technologies. There are NAWI teams at universities and national labs all over the US, and they are baselining what current water treatment technologies are in use and the water treatment landscape in general. So these baselining efforts are nearly complete, and the next steps involve various requests for proposals to promote new water treatment technology development. So the WaterTAP3 tool that I'm building is in the integrated data and analysis topic area, which you can see at the top left of this diagram. So in the NAWI framework, it will step in as a way to measure different technologies and strategies against each other and tell users many factors, but especially important are how much a treatment train will cost and how much energy it will demand. So this tool is needed because existing technoeconomic analysis tools for water treatment technologies don't provide a consistent cross-sector basis for evaluating the metrics that inform which treatment technologies are selected. So as a result, these other tools are rarely used to prioritize early stage research and development in water treatment. So WaterTAP3 will level the playing field for comparative technology analysis and for quantifying and tracking research and development impact on cost and sustainability and other relevant pipe parity metrics. And eventually it will be the industry standard tool for undertaking water treatment assessments. So here is a simplified version of how the tool actually works. We are capturing system level data about train design and costs, seen on this green side, and then also unit level data in the red to build each unit process. So unit processes such as reverse osmosis or chlorine addition, coag and flock, just any potential step of a water treatment train that a user might want. And then also the source water coming down in blue and its constituents. So then we're building a train based on the specified unit processes desired, the output water quality, minimizing energy use, and then outputting what unit processes are in the train, energy costs, construction costs, and a lot of other factors. So version 1 of the tool was written in Excel, and we are now coding it in Python, which adds flexibility and the ability to optimize and higher levels of accuracy to the results themselves. So when you're actually using the tool, the bare minimum inputs needed are the water quality, which is measured in total dissolved solids or TDS, and the flow rate of how much water you would like to be treated. And then the rest of the values in the model have default values based on the literature and data gathered by the NAWI teams. So these are the basics, like basic inputs. However, everything from membrane size to pump pressure to individual constituents in the water can be changed. And then these outputs are the levelized cost of water, or how much the treatment train costs over its lifetime per unit of water treated over that same lifetime. So then there's also the energy used in kilowatt hours, or the total energy cost based on the electricity rates where the facility is located. There's also removal rates and outlet water quality. And all of these output values are calculated on an entire train basis, as well as broken down by each unit process. And this tool is being developed for use by policymakers, planners, researchers, and interested members of the public, really anyone, and it'll be free and open source. So the tool is currently written and ran in Python, which isn't the friendliest to show, but eventually it will have a graphical user interface, which will be much more approachable for everyone. So I wanted to show you an example of some of the results from our baselining efforts. So this is a treatment train for oil and gas produced water. So the source is over here in Kern County, California. So the wastewater that comes from the production of oil and gas is treated along this train and then mixed with water for extra dilution, and then is used as its end use is to irrigate fields. So we built this train in Python and validated the tool's results with the actual data from this treatment facility. And this is an example of some of the results that you can have from WaterTAP3. So each case has a simplified summary of results seen here in the box, but there's a lot more results possible. This is just like a high level, kind of like those basic outputs that I showed before. And then all of these are also given for each unit process. So this is system level, but then there's per unit process as well. And the graph on the left shows an example of sensitivity analysis you could do of the data. So this one is showing an increase in TDS, that water quality. So more dissolved solids in the water. And you can see that the LCOW, so the levelized cost on the Y, increases, as well as the system recovery decreases with an increase in TDS level. So as you can see, these kind of graphs and sensitivities will help users get an idea of how the cost of their facility can be impacted. And the tool can also look at all different types of what if scenarios. So for example, if Kern County is looking at what if TDS increases and we want to add microfiltration and reverse osmosis. So seen here, adding a couple nodes, a couple unit processes to the treatment train, what will happen to the cost? And so this model will give a new train with new results, and then the facility can make informed decisions and informed cost decisions moving forward. So at the moment, we are continuing to validate with baseline case studies. We are adding optimization capabilities for optimizing recovery, energy use, or cost. There are papers being published for each case study and an explanation of the tool as we speak. And we are providing ongoing support of the creation and then the future analysis of requests for proposals. And finally, we'll be using the tool to test new technologies and the effect of adjustments to treatment trains to help support water treatment research and development, and to eventually increase society's water reuse. So I wanted to say thank you to the NAUI teams at NREL, and then to Zahi Kath at Mines, who's my advisor, and to the AES program in general for giving me the opportunity to do this research. And also thank you to all of you for watching this presentation, and feel free to ask any questions you may have or to email me later. Thank you.